Good morning, everyone. We're NU Paint Co., and as a disclaimer for our Capstone project, we did watch paint dry, but we did it proudly, and it's somewhat captivating. You'll see the presentation. But in other words, we developed environmentally sensitive hydrogels for quick drying paints. I'm John Gosbee. In the project, I led the economic decisions and analysis there, and then as well as I took charge of the analytics for the data that we collected.
I'm Kamm. I made the PFT, PID, and I also led the design of our control systems.
I'm Donal. I helped to flesh out the initial idea, and then I developed some of the testing methods and led some of the bench scale testing.
I'm V. I helped get a slab space, got the materials, led the safety analysis, and helped with some of the business entity.
So the main problem that we're trying to fix here is that a lot of paints in the industry now take a long time to dry, and they also have volatile organic compounds which can cause adverse health effects. So our idea is to make an electrically inducible paint that can dry through a different means in order to lower these VOC concentrations and to increase the dry times. So how we're going to do this, we're going to try to replace some of the latex binders in a normal paint with these electrosensitive hydrogels, which I'll explain in more detail soon. And again, it's to decrease the dry times and to decrease the VOC concentrations. So a little bit of theory behind how these gels work. Environment-sensitive hydrogels in general are polymer solutions in water that are going to morph, change the way that they're set up based on some kind of external stimulus. So in this case, for an electrosensitive gel, it's going to be swelling or deswelling with an applied current. And there's two methods that can happen with generally. Either the current is going to change the pH of the solution, and that's going to cause this gel to swell or deswell, or the ionizable groups on the back of the polymer chain are going to react to the current and change in hydrophilicity. And that's the type that we ended up working with for this project. So if you can see in the picture, these little areas are going to be spaces in between this gel matrix. If we can get those to contort and change shape, or just change charge and get the water to expel, that's how we're going to get the paint to dry. So when we were looking into it first, we wanted to make sure that there were applications that were similar to this to make sure it was a viable idea. So most electrosensitive gels are used in the pharmaceutical industry now in drug delivery. So someone will design a gel, they'll load the gel with some kind of drug, and then when this current is applied and the solution is expelled from the gel, the drug will go with it and be delivered to the patient. Hydrogels have also been used in paints before, usually for anti-fouling on marine surfaces. So they'll create a type of lipid bilayer so that stuff can't grow on the bottom of a boat. This will reduce drag and then reduce fuel consumption. But it's a nice thing to see because we are trying to put these materials into paints. So it's nice that it's been done already.
So for our business plan, we are categorized as an S corporation. This will help for selling stock to investors and provide assets and low tax incentives. So in the paint industry, there's about 4 large corporations that essentially own about 75% of the market. It's Sherwin-Williams, Valspar, Masco, and PPG. So then we're going to focus mostly on the specialty paint industry, and then that accounts for about 13.3% right now. And then we're looking to take up 1% of that 13.3%. So we're going to have to produce 7 million liters of paint per year. We're looking to run 330 days out of the year just to account for, something might go wrong in the process. We might need days off for holidays for our workers. And then each day we're looking to produce 21,450 liters. They're going to be run in 5 different tanks, not all in one batch process. So for marketing our paint, since it's a little bit different than other things out there, we're going to be really pushing that it dries faster than other paints and that it's electrosensitive, so that makes it unique to other paints. We're going to be selling it as a series, so it's going to they're going to be put together at the place where you go buy them. So you have the primer and the paint always next to each other, so you know that they go together. So then, since we're running a current through it, we're going to need an electrical device that comes with it. And when you go buy your first bucket of paint from our company, you can buy the package that comes with the electrical device, and that's reusable to run the current through. So then if you're painting another room or you need a couple cans of paint, you don't need to buy the package again, just the one time. And then to sell, we're doing direct to consumer, so people can buy directly from our website, or they'll be distributed at all large retailers that carry paint. And then one of the things as our brand, we want to make it super unique so that we can be acquired by a larger corporation. Since margins aren't super high in the paint industry overall, the best way to kind of survive as a company is to be acquired by one of the larger companies. It will also reduce our cost significantly. So then for distribution, we are renting part of a warehouse, not a whole warehouse, to have about 2 weeks supply in stock in case we have a sudden rise in demand or something goes wrong in our plant. That'll cost us about $275,000 a year. And then our shipping costs are going to be about 4% of the order, whoever's ordering. Then our largest upfront costs regarding distribution and packaging is going to be the line that fills all the cans. So that goes right at the end of our system, our final product's flowing and it just automatically cans everything. We got a quote for a line that cans 108 gallons a day, which is about twice of what we're looking to make, and a cost for that is $750,000 up front. We think ours might be a little bit lower, but we're just going with this estimate since it's what we have for now. And then the cost to fill each can, it's 12 cents each, 'cause it's the price of the can. Our plant's located in Georgetown, Kentucky. Kentucky has sort of like a middle of the road as it goes to tax rates. It's 5% corporates. And then we also pay Kentucky because of the mild climates, so it doesn't get drastically too cold or too hot. And while temperature doesn't affect our product since there's no reaction, it's just nice to keep things consistent. And then one of the biggest things about Kentucky is that that's where UPS is located. And since distribution costs are kind of like a large percentage of any business, we thought that it'd be great to be located near Louisville, as a lot of large corporations are right now.
So now that you guys have a little bit of background on our company and what we're planning to do from a business aspect, I wanted to talk to you guys about the design criteria and what our product needs to meet in order to be a viable product in the market. So first, from the paint aspect, it needs to be fast drying. Obviously, there are water-based paints, there's oil-based paints, and there's solvent-based paints. The current fastest drying paint is an oil-based or solvent-based one. However, those have high VOC concentrations, so we are going with a water-based paint and using the hydrogel to hopefully decrease the dry time of a water-based paint. We need affordable raw material. So the issue right now is that hydrogels are more expensive than the traditional latex binder that are used in water-based paints. So we need to find a hydrogel that is comparable in price. That way our can of paint isn't going to be sold for a drastically higher price than a traditional water-based paint. The availability of the hydrogel is also very important. As you can see, we're going to be producing a lot of the paint. So we need a distributor that is going to be able to provide us with enough hydrogel. The homogeneity of the paint. So paint, there's obviously no reaction occurring. It's simply a dispersion of a bunch of different materials. So is our hydrogel going to be able to be dispersed in the paint? That is something that needs to happen in order to have a viable paint product. And finally, the paint needs to pass all the quality control measures. So we have a list of quality control measures, which you'll see later, and it needs to pass those in order to be put on the shelf. The current application method. So how are we going to apply current to a wall in order to get the paint to expel this water? It needs to be easy for the painters to use, it needs to be easy for installation, and it needs to be reusable. So the cost of production of this system also needs to be pretty low. That way, when you look at a traditional paint and our paint on the shelf, there's not a huge difference in price. So I want to talk to you guys about the product and the manufacturing process for paint. So obviously, as been mentioned before, our product is an electrically inducible, quick drying paint. And what we're going to be looking at and talking about in a minute is the complete replacement or partial replacement of this latex binder. Looking at the manufacturing process, so paint is a pretty simple manufacturing process. You have a mixing tank filled with your solvent, in our case it's going to be water, and then you have pigment that is milled in. So our pigment is titanium dioxide. It's a common pigment in all paints. That's what gives it its nice white hue. The pigment has to be milled in because it's at a large particle size. Milling reduces the particle size and allows it to be dispersed more evenly and more properly. After this pigment is milled in and mixed with the water for a sufficient amount of time, you have additives. So you have biocides to make sure that there's going to be no bacteria growing in your paint when it's sitting on the shelf for days or months at a time. You're going to have defoamers to make it easier to mix. You're going to have surfactants and other additives as well. And then finally, at the very end, you have a step where you're going to introduce your binder, which in our case is the electrosensitive hydrogel. So here's a simple process flow diagram. Initially, we didn't understand the market that we were going to be targeting, so we had 2 5,000-liter batch reactors, but we realized that that's undersized for the market that we want to target now. And so as you can see, our design here has 5 mixing tanks to it. So I want to emphasize that this is just one system. There's going to be 2 of these identical systems in our facility. One day, paint will be mixing in one of them, and then the other day, it will be drained and being sent to the canning line. So as you can see, we have all the feedstocks here. They're going to be gravity fed because some of these are granular products. They're not all like liquid raw materials. Titanium dioxide is the only one going through that pigment miller there, and then being diverted to the appropriate tank. So our piping and instrumentation diagram, it's a little bit hard to see from back there, but as you can see, there are about 4 control systems. One of them to divert the raw material to the proper location, and then each of these reactors or tanks is going to be on a set of load cells. So in the paint industry currently, the simplest way to follow your recipe is to have the tanks on load cells. You divert the correct raw material to the tank that is necessary, and as the weight in the tank increases, you cut it off and go with the next raw material that needs to be added in the step. So something that I want to note in this is that all of our valves are going to be fail closed. We wouldn't want paint coming from the reactor prior to it being fully dispersed, and there's going to be no harm in having the paint sit in the tank. And then with the raw material valves, we're going to want those fail closed as well. That way we don't have any accidental addition of raw materials, and then therefore have to scrap a batch of our material.
Okay, so now we're going into our safety overview, and as Nick said, all of our valves are going to be fail closed. Based on the valves and pumps that we picked for our system, the max pressure that it can withstand is 5 atm and the max temperature is 70 C. Again, it should never reach 70 C though. The max it should ever be is around 30. But we will have temperature sensors on all of our tanks just in case we were to go 10 degrees below or above. Since there's no reaction, if there is a temperature change, it means something is wrong in our system and we need to be looking at that. So that's the main takeaway here. So our safer design, we're going to be minimizing the risk and minimizing spills. So we're going to have 5 small tanks instead of 1 large tank where we could be doing our batch process, and it'll also ensure better dispersion if we're running it in small systems. We, again, as we're focused on, we're reducing VOCs. So we're going to be replacing some of the additives and some of the binder with the hydrogel, which is safer. There's been a lot of EPA regulations that are just going to keep increasing, so it's very important for this. We are going to have our control and pump rooms located far from the process floor where everything's happening. And then again, our pressures and temperatures are going to be close to ambient. The water that's coming in for our system is just the tap water essentially from flowing in Kentucky. So it's usually whatever temperature in Kentucky is, which is mild. And then our tanks will only be filled to 85% to reduce the risk of overflow. And there's going to be level sensors there that are going to be monitoring that. So our SDS summary is here. Kind of the main takeaways here are going to be looking at the NFPA ratings. These SDS sheets are also going to be posted anywhere there's an entrance to the process room in case there was a fire and emergency. This is what the fire marshals would be looking at. Based on our numbers that we have, everything's pretty low. We do have a couple of health hazards for 2 of our chemicals, so we're going to make sure that whoever is loading the totes into the tanks is wearing like respiratory masks for the sodium polyacrylate, because that will significantly reduce the amount they're inhaling. Again, 2 is not super dangerous, but we do want to minimize the risks there. And then we have 1 on flammability, and it'll just kind of ignite if it gets to a high temperature. But again, everything's going to be temperature controlled, and it's just a raw material. So when the totes are coming in, we're not going to have a lot in stock as well. So the temperatures won't really affect anything. And yeah, for reactivity, everything's 0. So we should be, except 1, but we should be pretty safe, and the fire marshals will know that if there's an emergency, they can walk in, as we don't have any 3s or 4 that will make them question whether they are safe to go in the building. Our FEMA analysis, there's not a ton of risk, again, in our process. But the biggest things that we're going to be looking at are going to be the valves and the pumps, which are what are most likely to fail. Our tanks are just, again, overflowing, so we're going to have people walking by to make sure that everything's well. We have the level sensors in place, but again, just a secondary precaution, people will still be checking them. And then our valves, the seal around them can wear off over time, so they will stop working. So again, just weekly and monthly checks. There will be a signature log where someone has to check on that every week to make sure that everything is still as it should be. We don't want something to spill. And then kind of our bigger issue might be the pumps. They last about 8 to 9 months, but the lubricant inside has to be constantly replaced. So we want to make sure that we're also checking that, having a signature log to make sure someone is doing it. Because if the lubricant starts to run out, we could have failure in our pipes. And then there's also a rubber hose inside of the hose pumps. So that could wear off over time as well before the life of the pump, and that could be replaced. So again, just checking to make sure that all that is working. And then at the bottom of all our tanks, we're gonna have kind of a secondary containment area, as we've seen like in the UO lab, where there's like grates on the floor and it'll all flow into there just to prevent a large spillage in the room.
So for the actual experimental design, when we went in and did the benchtop testing, California Paints provided us with a lot of materials, which was very nice of them. They gave us a gallon of their standard semi-gloss paint, and they also gave us 4 gallons of that same paint, but without any binder added, which was great because this allowed us to tweak our formulations a lot more. We were trying to replace binder with the gels, so if we'd only had a fully formulated paint, we could only do so much. This way we were allowed to actually limit how much binder we're putting in as compared to gel, which was really nice. When we ended up doing the tests, we were shooting for high percentages of gel. We only ended up being able to acquire polyacrylic acid from Dow Chemicals, which is not as soluble as a gel we were hoping to use. So we ended up going with 0.1 and 0.4% by weight for our tests. When we did the tests, we used California Paints SOPs, which they provided us as well. We tested for mid and high shear viscosity, pH, and density just to make sure that everything was consistent with the paints that they'd had on the market. And we also tested drawdown, which is a different paint-specific test that I'll explain in a later slide. The dry time tests were the most important tests we were doing to actually make sure that there was some kind of proof of concept here and that dry times were decreased. What we did is we took each one of the percentages of gel and paint, and we would put some on drywall and some on sheet metal. So we would have 2 different surfaces of different conductivity. And then we would run current through one sample of each paint and not run current through another sample to have something to relate it back to and test against. So these are some of the pictures from some of the tests that we did. To the left, all the way, is this drawdown test. And basically how it works is up at the top here, there's 2 divots. And the divots are thicker. It's 5 millimeters here and 0 here. So you'll put a little drop of paint on, draw it down, and if the paint starts to streak or crack at a certain thickness, then you know how thick your coating can be, basically. And the paints that we made actually worked out really well with these. They were very similar to what the original California Paints had. As you can see in the second picture in the middle, this is with the current going through the paint. We wanted to make sure that current was actually passing through paint and that this was happening, so we got a voltmeter. We were using 9-volt batteries. This reads 8 volts now, and we're assuming that's either because the batteries don't actually have exactly 9 volts or just over the time of testing we probably used up some of the charge. And then all the way to your far right, that's more of the dry time tests. So these top chunks here are pieces of drywall that we cut out, and then the bottom are the sheet metal, and that's without any current to get more of a control group.
So looking graphically at all of these experiments that we did, we categorized everything basically by the weight percentage of the hydrogel. So at 0.1, 0.4, you can see the blue bars here represent the dry time with the drywall, and as a general trend, the addition of hydrogel decreased the dry time without voltage, and this is primarily due, we hypothesize that this is because the hydrogel is essentially the binder in the paint, and so it's just making its way more to a typical paint. And the gold yellowish bars are the dry times with voltage. And I don't know, it's subtle, but I don't know if you can see, I want to point it out, at 0.1% is actually the minimum dry time that we observed. And we think we have two hypotheses with these, and the first is that the addition of the hydrogel to dry time is characterized on a logarithmic pattern. We think this is unlikely, and we don't have enough data to back this up, so we kind of disposed of that. And the second theory is that the battery that we used discharged enough of its voltage or enough of its charge to essentially, when we were testing 0.4% hydrogel, it was essentially running at a lower voltage than that the 0.1 percentage was. So we think that's more likely, and that's what happened. So for the next slide. Again, further experimentation with, we did all of these experiments at Chase Corporation, and we worked there previously, and we had access to as many materials and equipment as we wanted, essentially. It was a quiet Friday afternoon, so we had the time and the resources to do it. So following the California paint SOPs, which were given to us, we just simply measured the viscosity and the density of each of these paint formulations, and the general trend was with the addition of the hydrogel, the viscosity and the densities were increased as well. But one thing we didn't find was that maximum density in which paint cannot be considered paint anymore because it's too thick to apply to a surface. So further testing, we would want to try and find that upper limit and see if, just to observe our operating limits or our testing limits for that. So with the economic analysis, Aspen provided us with some data with RO system and the tank, not the milling. We found that Aspen didn't quite help us out in this regard because it was just a batch process, and we decided to take the analysis into our own hands. And so you can see with the equipment costs, the most expensive piece of equipment is the milling line, and that's not included in our PFD or PNIDs because it's not part of our chemical process. It's more of a downstream secondary thing, but it does represent the majority of our equipment and install costs. And then in the bottom right hand corner is our cost breakdown per batch. So essentially it's our recipe for making the paint and the corresponding costs of each ingredient. And as you can see, the titanium dioxide, which Nick mentioned, is our most expensive raw material, and is our pigment, is our most expensive raw material, and that's about $1,500 per batch. And there's no way of mitigating this, just simply because it's necessary in all paints. From there, we calculated revenue, margins, and profits, and so with our production estimates and our estimated sale price to retailers at $8 a gallon or a can, we can realize $15 million in revenue per year. Our variable costs and operating costs take everything into consideration, from labor and supervision all the way to taxes and rent, everything like that we learned in Capstone 1. And the tax rates are based off of the 21% federal corporate tax rate and 5% for Kentucky state tax. And furthermore, our discounted cash flow schedule shows that with an initial investment of $12 million, as shown in the first year of the cash flow, the initial investment is worth, has a net present value of $15 million and an internal rate of return of about 32%. So these are attractive numbers. Of course, an IRR of 32% is quite high, but with our assumptions, we're quite confident in all of this. And the depreciation schedule follows a 7-year Macker's pattern, and that's essentially to offset the taxes to further years, so that we can have more cash flow during our startup years.
Now, just to summarize everything that you've heard in this presentation, the final desired product would be a paint that would have 20% of this hydrogel. As you can see, our testing didn't allow us to reach those high concentrations of hydrogel just due to the nature of the free hydrogel material that we were able to get from Dow Chemical. With resources, with money, we would be able to experiment further with a better hydrogel material, but those weren't available to us. So the polyacrylic acid hydrogel test, they did decrease the dry time when a current was applied. The theory would be at higher concentrations, and with a better hydrogel, we would be able to see this trend continue. However, it did increase the viscosity and the density of solution, so there could be an upper limit to how much hydrogel material that we could add. We might not be able to achieve that 20% that we desire if the density were to increase too much, and therefore you wouldn't be able to spread the paint. So we want to select some additional hydrogels for testing. We did actually secure an additional hydrogel that we can test, but due to timing, we weren't able to test it yet. And then one possibility that we thought of is to mill the hydrogel. So if we could decrease the size of the polymer, it would reduce the agglomeration, hopefully reduce your viscosity, and we could see some benefits of doing that. But we really think that with an investment of $12 million for our initial startup, we could invest enough money in R&D to really get a working product and find a product that is cleaner for the environment, one that will reduce dry time, so it could help a blue-collar painter and decrease the VOC concentrations in paint. So with that, we'd like to acknowledge a couple people. Professor Pfluger for all of her hard work this semester and for all of her help leading the direction of our project whenever we had any questions or any concerns. Jason Trout with California Paints. We contacted him early on in the semester, and he was excellent. He didn't go to Northeastern, doesn't know anything really about the co-op program, but he just remembered being in our shoes and needing help. So he was able to lead us in the right direction, give us some great materials to work with, and give us their SOPs. Chase Corporation, they were fantastic. They allowed us their lab space to use anything that we needed. They were there for help whenever we needed them. Anthony Fusco, our advisor, he was there. He lended a hand whenever we needed help and was always reaching out to us. And then finally, just the chemical engineering department for our education and for everything that they've given us over the last 5 years. So with that, we'd like to open it up to some questions.
Thank you.
Question. If you were to paint a house with your paint, how would you apply the current to say a wall?
Yeah, so that is something that we have it theorized, and it's something that definitely, if this were going to progress farther, it'd be something that we would develop with engineers out of our discipline, so with electrical engineers. But the theory is that you'd have basically 2 strips on either side of whatever size wall, right? So say this wall, you have a strip on this wall, a strip on that wall, and it'd run from floor to ceiling. And then you'd have a power source that would connect to it. So you'd have anode and cathode, and you'd send the current through the wall. And because the hydrogel itself can transfer charge, you should be able to get a current running through it, regardless of the material, whether it's sheet metal or whether it's drywall. You should be able to get a current through it just due to the nature of the hydrogel.
Okay. And it honestly, it's nice that it works with low enough voltages and currents that if you do have wiring behind the wall, it's not going to, jump charge or anything. It's not going to mess with stuff that's already in there.
And obviously safety is a concern as well. Mm-hmm. So how much current, how much voltage you have running through this wall. Obviously, we had a 9-volt battery running through. I know it was a much smaller distance, but in theory, you wouldn't need anything over 12 volts, and so it should be safe. And especially if you're going to have some sort of contractor applying it, they would understand how to use it, and you're not going to have to apply the current for very long.
Okay.
What was your rationale for using a batch process instead of continuous?
So they don't actually use continuous in the industry because paint is just a dispersion. If you use a continuous process, you're not going to get the consistency that you would from a batch process. So that was what led us to, you're going to basically have variations in your paint if you use a CSTR or something like that. So a batch process is how they do it in industry, and it's definitely the best proven method.
Thank
Good,
you.
thank you.